Standing waves. Standing waves or stationary waves, as the name implies, is a wave that remains in a constant position. This phenomenon can occur because the medium is moving in the opposite direction to the wave, or it can arise in a stationary medium as a result of interference between two waves traveling in opposite direction. In the case of the second example, the waves of equal amplitude traveling in opposite direction, there is on average no net propagation of energy. So the waves, the places on the standing wave where there is zero amplitude are called wave nodes, and the places on the standing wave which have the maximum amplitude are called antinodes. So propagation of energy in standing waves. Because there's no motion of the wave, there's no net transfer of energy from one end to the other end in a standing wave. And points vibrate with different amplitudes, ranging from 0, which are the nodes, to a maximum antinodes of maximum amplitude. The reason that no net propagation of energy occurs in standing waves is that the energy cannot flow past the nodes in a string towards the right or the left. Hence, the energy is said to be standing in a string, although it alternates between vibrational kinetic energy and elastic potential energy. At the antinodes, the energy is nearly entirely stored as elastic potential energy associated with the stretching of the string. And this is represented as time t equals 0 and as time t equals 1/2. At time t equals 1/4, nearly all the energy is kinetic, and here the period, where t is the period of the system. Standing waves in a string are given by this formula, F equals V over lambda, and you might think this is a new formula, but actually it is not. Rearrange this as V equals F lambda. This is exactly the same formula as we have been using for the string. Okay? So for a standing string, there are different modes that people talk about. The first one is called a normal mode. In a normal mode, there are no nodes in the vibration. The first harmonic is where there is one node, and then the second harmonic is where they have two nodes, and so on and so forth. The frequency in a standing wave is given as V over lambda or V over 2L. Here's a graph that explains what it is. For the first mode, the wavelength is 2 times L. So note, 1 times L goes from here to here, and the other time the L goes from here to here. So total length of the string, the wavelength, is 2L. In order for this 2L to exist, the frequency is going to be given by the speed divided by twice the length. And the harmonic will be this one. For the second mode, which is the first harmonic, the wavelength is L, goes from here to here and here to here. There are 2 waves in it. The frequency will be V over the length of the string, and the harmonic will be drawn like this. The wavelength for the third harmonic, so for the third mode or the second harmonic, is 2L over 3, and the frequency correspondingly is 3V over 2L, and the harmonic is given like this. So for the fourth one, the wavelength will be L over 2, frequency will be 2V over L, and the harmonic will be given by this. So I'm going to leave that as a homework for you to calculate the fifth wavelength, the frequency, and sketch the harmonic. Now, here's a question. Calculate the speed of a standing wave in a 90 centimeter long guitar string with a fundamental frequency of 400 Hertz. Now this is a very interesting question. So it's asking us, we have to calculate the speed of a standing wave in a 90 centimeter long guitar string, and it has a fundamental frequency of 400 Hertz. Now the first things first, what is wrong with this statement? First thing that's wrong is that it's not given in SI unit. So in SI unit, 90 centimeters will become 0.90 meters, right? With a fundamental frequency of 400 Hertz. So how do we solve this problem? We know speed equals lambda F. And previous slide gave us lambda equals to 2L over N, where L is the length of the string. So in order for me to solve it, I'm going to put the lambda here as 2L over N times the frequency. Now N for the first harmonic is 1. So I plug that N into here. What do I get? I get 2L times F. 2 times L, which is given as 0.90 meters, and frequency, which is given as 400 hertz, equals 720 meters per second. Allowed and forbidden standing wave conditions. So very carefully look at the allowed and the forbidden standing wave conditions. So allowed conditions are that nodes should exist at the ends. So each of these nodes has to have an end point at the end. So forbidden condition would be something like this, where the wave goes beyond where the end point is, or the nodes go beyond the end point. That is not going to be an allowed condition, or the wave ends early. In these kinds of cases, the wave just dies off and it's damped very, very quickly. Overtones, harmonics, and partials. So for a string held tightly at both ends, it is only allowed to vibrate at particular frequencies and wavelengths. The whole string can vibrate up and down, which is called fundamental frequency. The string is also allowed to vibrate with harmonics of fundamental. For example, it may vibrate in halves with the nodes at the middle of the string called the first harmonic with frequencies equals to 2F0, or in thirds or fourths or in higher. All harmonics as well as fundamental will always have nodes at each end. Any wavelength that does not have a node at each end of the string will not form a standing wave on the string, hence it will be forbidden. So harmonics are whole number multiples of the fundamental modes. Overtones will be all higher modes of the fundamental modes, and partials include all modes or components. Partials include all overtones and harmonic. And all together, they will form something that's called a spectrum of vibration.